Thanks a lot, everyone, for joining. So I've been doing ESTCube for 12 years, and for the last year or so, we've been doing something quite challenging, I would say. And this has been trying to make a mission design that could fly into lunar orbit, and trying to do it with a CubeSat, and with the main goal to test the electric sail. The idea has been around for more than 10 years. In one of the ESTCube-1 workshops in 2013, Pekka and Mart was suggesting this, and I kind of felt that I would like to do it after ESTCube-1 or something like that. So as I will show in the slides, then has been, has been on my mind for a long time, and thanks to Antti and Michael and many others for supporting this, we've been able to make it. As you see, many contributors. I guess I'll not introduce what everyone has done. I'll just say that it's been a big teamwork with many professors and also many students and a couple of high schoolers as well from Estonia and Latvia. All right, so some known slides, but just to go over the topic again, that we have different kinds of propulsion systems. And if we take the conventional systems of chemical propulsion and electric propulsion, then there's certainly need for a tank. And if you look at Cassini spacecraft chemical propulsion, then basically the tank serves as a structural element for the spacecraft. And then with the electric propulsion, the tank is smaller, and they use smart methods to accelerate gas particles, but it also comes with the larger solar panels. And that is you can see it on Rosetta spacecraft. Then we have light sails, which is something like Icarus has tested already 10 years ago. And also quite amazing system, but we need to deploy them in 2 dimensions. And then thing we've done for some time already is eSail, where we have, with Yaroslav and many others, we've shown that it's possible to make it with a single tether on a CubeSat, and even maybe to go to asteroid belt. But that's just a concept. Also, this is a conceptual drawing that inspired me more than 12 years ago when starting to prepare for my PhD studies. And Urmas Kvel was writing my PhD application around the time, helping me to get on board in Tartu. But a bit of longer history here is that in order to make a propulsion system, we first have to find like some kind of physical basis for that. And in our case, that's solar wind, based on which we can make magnetic sails, electric sails, and there are other new inventions around that I won't discuss here, but anyway, just putting it out there that different types of solar wind propulsion methods are used. And then along the way, Pekka also invented the plasma brake for deorbiting in low Earth orbit. And actually, most of our work has been focused on testing the plasma brake technology in low Earth orbit. So we had first experiments on ESTCube-1 and Aalto-1, and then a range of experiments on AuroraSat-1, 4Sail-1, ESTCube-2. All of them had some different problems, and 4Sail-1P will be relaunched, and with ESTCube-2, we're still waiting for the investigation. I'll tell about that later. So then 4Sail team wants to go to the highly elliptical orbit, and it's just now 4Sail-2 satellite. So a bit of history there. And now we can use the moon as a playground to test electric sail in the solar wind and do it in kind of more forgiving environment than truly deep space, as we would go to the asteroid belt or further. Right, I mentioned my PhD application. So this is the original document. Urmas wrote it. And basically, the idea was that I would advance some ESAL missions. One of them was about asteroid touring. And that's actually done. I went to the NASA Ames Mission Design Division to do that. And then there are some other, let's say, non-Keplerian ideas what to do with ESAL. And actually, University of Pisa has been advancing those in recent years. And I kind of went on with ESTCube-1, ESTCube-2, and oftentimes mission design was left behind. Right, we all know this project. Just for the record, we built ESTCube-1 during 2008 to 2013. Then it was launched, operated for 2 years. It had the first electric sail experiment. Unfortunately, it did not deploy. And have published a lot of papers about it. And basically, after that mission, we went on building ESTCube-2, which was a huge challenge. And because starting a new project and starting the second project where it wasn't clear what and how we should do it. But anyway, after 8 years, we managed to launch it, and a lot of support from our partners, from EU and also from ESA. Unfortunately, the satellite got stuck on the rocket. It's not official news yet, but yeah, we're waiting for investigation results, but most likely that is the cause of, that's what happened with ESTCube-2. This is the ESTCube-2 team as of a bit over a year ago in Teletorn, in Tallinn. We were celebrating sort of a media campaign for handing over the satellite, although the satellite remained in Estonia for still a few months. And then Jaroslav has made this nice video where he shows that how this core technology on ESTCube-2, the plasma brake, how it looks. It has different parts. I'll not go into detail now here. It's published in our papers, as I'll show. The main point with this video is that there's no propellant tank. So basically, as long as we can keep on charging the tether, we can keep on running the plasma brake or the electric sail. Doesn't depend on the size of the tank. Yeah, and basically the model that you saw comes from this paper written by Janis, published this summer, I think, or spring. And it was part of the special issue for advances in CubeSat Sails and Tethers, but because of some number politics, it got taken down from that. But instead of that, we'll have Petri's article on the whole plasma brake module, which is under review now. At the same day, when we met for the ESTCube-2 delivery, also made this photo with the ESTCube-1 people. And it was very warming to see that after so many years, we can still, come together and be good friends. And actually, a few minutes before or after we talked with Johan, before or after this image was taken, we talked with Johan, and he'll show results that he made, that basically the idea was discussed in Teletorn. And you can see Mario will also be talking today. Right, talking about Mario, this is what we published in summer, actually. Long story short is that Antti gave me an opportunity to work on ESAL for a couple of years, I guess, by now. And getting Mario as a PhD student was big foundation for that, as he understands physics and wants to do ESAL and also knows programming. So it's the first step in modeling ESAL on Tartu side, on Estonian side. And again, long story short, we can bring this work like a Coulomb drag modeling into orbit propagation and make more complicated systems than in this paper. All right, we have arrived at the main topic of today's talk. And I'll show a few experiments and a few technological solutions we designed during the last year or so. Okay, the basic idea is here that in the lunar orbit, we would like to characterize the thrust, measure the thrust of the electric sail as caused by the Coulomb drag interaction with the electrostatic sheath created around the cell tether. That's, I guess, more or less everything in this image. And the rest is about, yeah, what kind of polarities we use. We use positive polarity and electron emitter to keep it all positive. And this is, in this kind of mode, you can, I hope it's clear in the image that the spin plane is perpendicular to the solar wind. So we are having the most thrust as pushed on the spin plane. And we can also do this if the spin plane is parallel to the solar wind. And with that, we can, instead of generating thrust, we can generate torque, which results in the change in the spin rate. And basically, we had the same image in ESTCube-1 paper. We had the same same formulas in the ESTCube-1 paper, and we had to update this for the ESTCube-LuNa case. And but before we can do these experiments, you actually have to deploy the tether, and that's of course very challenging. And for that was the thing I asked Johan to help with. So Johan, if you can, maybe you can explain these graphs and tell what you've done in the simulations. And feel free to take as much time as you need.
Hi, good evening from my side as well to everyone. Yes, so as Andris said, he approached me with a request to simulate the tether extension dynamics. And I'll try to give a quick overview of the results on the plots here. So if we start from the bottom right, the four small plots, that basically just shows a generic extension of the tether in several steps. Out of the four small ones, the bottom left shows the tether tension. So we were given, let's say, the required tension limits from Pekka, the minimum that is needed and the maximum that we can use. And basically then the angular velocity of the satellite will just oscillate. So, or let's say, you will extend the tether, the satellite slows down, you speed it up to increase the tension again, and so on. Just monitoring the tension to keep it within the required limits. There is one interesting case that came out. If we look at the top right section, normally when we extend the tether, we assume that the satellite angular momentum slows down, and therefore the tether tension also goes down. And this is clearly visible on the bottom graphs. So each of those sharp steps, as the tether is extended in a short time period, the tension goes down. Now in the top right corner, let's say the second row from the top, you can see a very clear and a significant spike in tether tension at approximately 3 days. So the time isn't that important, but what happens there is that as the tether as you start to extend the tether initially, the tether length increase, let's say relatively in proportional terms, the tether length increases considerably more than the satellite's moment of inertia. which slows down the satellite. So basically, because the end mass radius with extending the tether increases a lot, relatively again, then the tether tension initially will go up quite significantly. So this is one of, let's say, one of the areas that really needs to be monitored in terms of overstressing the tether during the initial deployment. And then for me personally, I would say the most interesting plot is the big one. And as far as I know, none of these detailed simulations have been run for any of the ESTCube tether projects. So the top one shows the oscillation of the tether as it's being deployed. So the bottom right plot of the big ones shows that as we start to extend the tether, it starts oscillating, and the oscillation amplitude goes down as the tether tension increases. And then when the tether extension is stopped, so initially, as you can see, the average is -5 degrees. So the tether lags behind the satellite. And then when the tether extension is stopped, then the tether continues to oscillate with the same amplitude as the average was before, but now around the side panel normal, so the extension axis. So these are let's say these for the real actual case, these need more detailed analysis, but quite interesting results. And as I say, as far as I know, these haven't been these kind of simulations haven't been run before. So quite interesting work there.
Yeah, thanks a lot, Johan, for your work and for the little summary here. Indeed, pretty challenging in terms of control and dynamics. And I guess this will be a theme throughout the rest of the presentation, that is, we're kind of scratching the surface of how difficult these problems are. And even if we forget about ECEL, then you'll see some other challenges that are, from space technology, pretty cool to address. But before we go to this, so this is, if you think about the thrust experiment where the spin plane is perpendicular to the solar wind, then when we are in lunar orbit, and I'll not go into detail why, but our spin plane remains inertially fixed because it's easier from control point of view and from satellite design point of view. So there isn't much like trajectory alteration or maneuvering we can do with this kind of setup. But what we can do is, as you can see on the top left, we can charge the tether on for example, on one side of the orbit as the satellite goes towards the sun, and this is represented with red color. And then again with the red color down here, I hope you don't see construction work in the background. With the red color down here, you can see how the orbital period changes. And basically, we're running this for some 3 days, and we have the change in orbital period in 100 seconds. And that's quite a lot in terms of, characterizing the orbit and saying whether the change has happened or not. But of course, we don't have like this reference satellite, the blue graph here in real life. So the change will not be that clearly visible. But anyway, it is significant even with a, let's say, modest ECEL. And another thing we can do is monitor like what Johan said, there are a lot of dynamical behavior that is difficult to understand, difficult to model. And we would certainly like to have some in situ data on that. So basically, Mario made this render where the tether is seen as it will be seen from the satellite with a camera by Crystal Space, for example. But it's just plus minus 45-degree camera. All right. So we're going into the technological challenges. I mean, going to the moon, amazing, but also very difficult. And there was Artemis 1 mission with several CubeSats, 12, I guess. And I guess I'm not lying if I say that most of them did not fulfill their mission, including the Neo Scout, which was a light sail developed by JPL, I think. So yeah, very challenging, and we should be taking our lessons from that. But there are even more challenges if you're not a space agency. So we don't have deep space network, for example, for communications. But yeah, just to summarize, when you talk about CubeSats in low Earth orbit, and that's something like ESTCube-1, something that ESTCube-2, where ESTCube-2 wanted to be, we have many options for communications. A lot of universities have ground stations and so on. And there's Earth magnetic field we can use for attitude determination and control. Then when going into deep space, then these conventional satellites like Cassini, like Rosetta, they use deep space networks. And they use deep space networks not only for communications, but also for navigation. Yeah, actually, Vilios and sitting there has been helping Rosetta with some ranging, I think, or communications as well. And they require propellant for maneuvering. So the light sail that I mentioned earlier on Icarus has been tested on just a couple of satellites. So mostly it's chemical and electric propulsion. And then if we want to take nano satellites or nano spacecraft to deep space, then we need new communication solutions. And we need to think how to navigate and how to propel and so on, and how to control the satellite. So in the next slides, we'll show some examples of our ideas, how this could be done. Of course, very futuristic, not ready to be developed, but in terms of opening up research topics, I think this is a very, very fruitful ground. All right, for the concept of operations, this slide includes a lot of details, but I'll try to point out the main ones here. So first of all, the first problem is navigation, communications, and I've been working with Ventspils, also my alma mater, that we could use their radio telescopes that are now being repurposed for uplink and downlink. And there are two of them, just 16 and 32 meter ones with different availability. And now already an outdated image, I realized that we plan to use 3 meter dish in Estonia, in Terravere, operated by Viljo for UHF communications, but then Janis later realized that we have to use Yagi antenna. So this is already wrong. And yeah, with the big antennas, the plan is to use a X-band, and with the smaller antenna, the plan is to use a UHF. And for navigations, again, Johan helped out estimating if we can do optical navigation in this cis-lunar system with the moon, Earth, and the sun visible for a lot of the time. And we estimate that it's possible to do it with tens of kilometers accuracy, Johan estimates, and we also get some 1 degree attitude out of the solution. Very early, very, as Johan says, very brute force method. And yeah, what else is here? Anyway, let's go into some details. And now, if Katarina is here, you can talk.
I'm here. Hello.
Yeah, hello. So please.
Okay. Andris slightly touched the communications part already, but I'm going to talk more in detail about this. Overall, the communication subsystem or communication system has many challenges. For example, like delay of more than 1 second or minutes long periods of communication blackouts, etc. That all is because of the lunar mission. So also periods, extended periods without direct sight between the lunar spacecraft and the ground system, etc. But for these solutions, we propose like communication that like telemetry and command part is doing the turnstile antenna on ultra high frequency or UHF band that would cover the whole sky, and this would be used for regular spacecraft monitoring and telemetry and like control from the ground. There's one like solution from EasySpace that can be seen on the right of the slide. Maybe Andris can point to it. If you, okay, never mind.
I tried.
Okay, I can talk about it more a bit later. But for the data downlink, we propose a solution like in total of 6 like patch antennas. 4 of them would be transmit only for improved downlink, and a pair of transmit and receive patch antennas would be used for the ranging experiment, and these would be placed opposite to the E-cell experiment. Also, Andris wrote to the proposal that they can also be used for the firmware upload or emergency firmware upload. Overall, the communication system consists of low speed communication and high speed communication. For the low speed communication, there's a Yagi in Teravere, and for on the antenna on the satellite there would be that turnstile antenna. This is near isotropic antenna system. That means there's no blind spots. And yes, this is the like it consists of cross dipoles. That is on the right of the slide. And for the high-speed communication, Andris already talked about the Ventspils Radio Astronomy Center ground parabolic dishes. There's 2 of them, RT16 and RT32. Respectively, they are 16 meters and 32 meters in diameter, and they're repurposed for both uplink and downlink solutions. And on the spacecraft, there would be, for example, EnduroSat expand patch antennas. These are very small, which is good for like that means there's could be more power production on the satellite.
Right. Thanks a lot, Katarina, for the summary. And there's a theme here that we have to place the same component on different sides of the satellite, because we're far away. The moon is orbiting the Earth. We're orbiting the moon. The satellite is orbiting the moon. And then the satellite is also spinning. So Katarina mentioned several patch antennas on different sides of the satellite. And then a similar thing is with the navigation cameras. So you can see this ESTCube-1 spin-off camera from crystal space, really tiny one. And then we can place 4 of them in these 2 tuna cans, another one on the other side of the satellite. So 5 navigation cameras providing the solution I mentioned earlier. And attitude control was probably the stuff that was keeping me away from advancing this mission design, even kind of in a very idea sense, because I just knew that it's not possible. Until a year ago, Martin Timer was visiting us and showed that he has developed and already tested these thrusters. So basically, hair-thin, sorry, not hair-thin, but finger-thin or thick thrusters you can place on one unit CubeSat, bigger CubeSats, and they're very good for attitude control. And their efficiency is crazy, something like 4,000 seconds, although the thrust is very, very small. So the simulation that Johan showed is probably taking hundreds of days to deploy the tether. All right, is Gustavs here? Right, Gustavs is not here, I guess. So I'll show an amazing work here by a pupil from Latvia, Gustavs Plonis. Basically, he took the Unreal Engine 5 and made the first proof of concept that we can place these celestial bodies, the moon, the sun, the earth, in some kind of orbit. Well, currently we have a pre-program orbit, but we're working on to integrate that with orbit propagator. So basically, if we get orbit propagator working, and we place these 5 cameras on the satellite, I don't see a reason why we cannot write navigation algorithms on this, at least some kind of preliminary thing. And maybe it's hard to see because Gustav's tried to make everything in one picture, so there's sun and celestial bodies in one picture, but anyway, you can see something. Now, I mentioned Mario several times, and he has been touching almost everything I showed here in one way or another. What is Mario doing now is actually also another cool thing. So he's making the mission video. So Mario, please, you can tell what is in these slides, and I can click to the video when you're ready.
Yeah, sure. Can you hear me all right?
Yeah, very good.
Okay, perfect. So now we are working on the ESTCube-LuNa mission video, and the objective is both to show what ESTCube-LuNa can do and also make the video stand out a little bit among all the space mission videos that, in my opinion, they are all the same. So that's why you see both some artistic imagery and also a visual representation, artistic scientific representation of the solar wind. And yeah, the video will be ready in a month or so, but for now we've brought a draft of the video and hope you enjoy. You can play it.
Yeah, thanks a lot, Mario. And there's music from Richie as well. All right. Thanks a lot, Mario, for this. Amazing to see some of the craziest ideas to realize in some 3D world, at least. Right. Some final, I guess, notes here is that in May we celebrated 10 years since ESTCube-1 launch. Amazing event here, right here where I speak now, in the observatory. And yeah, we were anticipating ESTCube-2 back then, and how amazing it will be. Was not. So, but anyway, nothing is stopping because we continue with collaboration. Just a month ago, there was a huge crew from Ventspils here, and we talked about collaboration in ESTCube-LuNa, in Comet Interceptor, FPJ development. So yeah, I guess our space tech has grown much bigger than ESTCube, and we can move on anyhow. So this is the consortium for ESTCube-LuNa. Yeah, I won't be boring telling what each of these partners are doing, but it's a lot of science and technology that is basically each partner is bringing in a component without which it would not really hold together. Here's some references from the blog. This talk was based on the article we submitted for the advances in CubeSat Sails and Tethers on ESTCube-LuNa. As soon as the paper will be out, we'll publish these things in the blog as well. I mean, there is something preliminary there, but I guess the update would be much more interesting. So thanks a lot for your attention. I guess we can go to questions now, if there are any. All right, no questions? All right, then thanks a lot for your attention. Thanks, Mario, Johan, Katarina, for filling in. And yeah, let's see where this goes. Very early work. And of course, as I said earlier, this is just scratching the surface of a lot of new exciting research topics in space tech. Thanks.